in engineering physics. Oh, sorry, I should record it. Right. Oh, it's recording.
I just started it.
Yeah, sorry, but I forgot it. Thank you. Yeah, Benedict recently completed his PhD in engineering physics at Embry-Riddle Aeronautical University. His research focused on numerical and theoretical modeling of acoustic gravity wave and transport phenomena in upper atmospheres. He has worked on problems related to energy dissipation, nonlinear wave dynamics, and multi-species diffusions with application to Earth and other planetary environments. He's also spending time at Los Alamos and Sandia National Labs, and has an interest in connect physical models across scale and disciplines. So yeah.
You want to sit down for this, I guess. So thanks for coming, everyone, online and in person. My name is Benedict. I work with Dr. Jonathan Snively and Roberto Sabatini. And yes, I will do a presentation on modeling acoustic gravity wave propagation. I want to start off with a general background, and I kind of like to describe fundamentals, even if it's a little bit repetitive, so maybe that's the place that you'll take a nap. And then we'll go into diffusion processes in the upper atmosphere, which is kind of the focus on my PhD. I'll give you a mathematical description of it, linear and nonlinear analysis, and describe some results and how they can be applied. Begin with general background. So Earth's atmosphere can be described as a compressible dilute gas, exponentially decaying density, comprised of primarily nitrogen, oxygen, and atomic oxygen, at least below the thermosphere, and in the thermosphere inclusive. It's segregated by 5 layers of interest, and there in these 5 layers of interest, a wave experiences amplification, dispersion, reflection, and dissipation. And here I have some figures depicting the Earth's atmosphere. On the left, we have mass fraction with altitude, and on the right, we have pressure, density, and temperature with altitude. And in these boxed regions, I have transitions of composition on the left, where the Earth's atmosphere goes from primarily nitrogen, and it begins to become dominated by atomic oxygen. And on the right, we have a box region for the temperature gradients. So there are some properties which can influence the dynamics of the upper atmosphere specifically. And this kind of sort of description of an atmosphere applies to any sort of atmosphere. So this is not only discussing Earth, but we can talk about any planetary atmosphere, where if you have the neutral atmospheric properties of it, temperature, pressure, density, and mass fraction, then you can describe or at least paint a picture of the dynamic processes. And so what I mean by dynamic processes is some sort of introduction of energy into the atmosphere, which induces some oscillations, which is what we talk about as waves. Here are some sources of infrasound, and on the left and on the right, we have sources of gravity waves, and some they're not mutually exclusive. So you have rocket launches, earthquakes, anthropogenic sources equaling to bombs, etc. And so when we describe atmospheric waves, we divide them by their frequency content. So we say that acoustic waves are dominated by compression, and internal gravity waves are dominated by buoyant or gravity forces. And so again, here's a picture showing the segregation between the two, and they are separated by Brent-Weissler frequency in the case of gravity waves, and acoustic cutoff for acoustic waves. For acoustic waves, they would be again these compressional longitudinal sources. Here's an example of one. I think it should play. You have this longitudinal where the energy of the disruption equals to the direction where the wave propagation is. These are of interest to my team and to many people as well, especially for infrasound. For internal gravity waves, also of interest to people. These again arise due to the buoyant or gravitational forces, and these require a stratified fluid in order to exist. So that's an important case of it. Here I want to show sort of another video for visualizing internal gravity waves. So you have some sort of diaphragm in this stratified liquid. This is a simulation, so all those layers are kind of relevant. But the idea is that you have a moving diaphragm, which represents your perturbation, oscillation, introduction of energy into the system, and then the transverse, sort of the diagonal oscillations are how you get it, as opposed to if these were acoustic waves, the propagation would be only in the direction of the oscillations. So we characterize atmospheric waves through dispersion relations, at least for the linear ones. So linear waves meaning like you have a superposition of waves that describe your wave, and we have dispersion relation. This relates the angular frequency to the wave number. For a non-dispersive wave, you can see that if you break down, transform your wave, everything has the same phase speed, versus if it's dispersive, then it is a nonlinear dispersion relation, and it has the phase speeds of each of the waves are different, or can be different. From this dispersion relation, you can also obtain an attenuation coefficient, and this is an important sort of distinction, because I will discuss the results of some of them, but this attenuation coefficient, this is related to absorption processes. So you think of viscosity, think of thermal conduction, and I'll go briefly over that in a second. But this is important because this describes, at least for linear waves, the exponential decay of or the spatial exponential decay of a wave. So for the thesis and for part of the presentation, the question would be, what are the dispersion and dissipation processes affecting vertically propagating waves? And this is for source classification. This is for if you just have a pure scientific interest in what's going on below some sort of atmosphere, or below an atmosphere that you can't see and you just remotely sensed it. You need to have all these dissipation processes to describe them, especially in the upper atmosphere. So I'll describe very briefly diffusion processes. So when you're thinking diffusion, we're thinking about sort of like things that increase entropy. We can think about things that disperse energy as well. Momentum diffusion due to viscous stresses. This is viscosity. Heat conduction through or heat diffusion through heat conduction, and then a new one, or one that hasn't been, I guess, paid attention to, is species diffusion. So this is sort of the movement of species or different molecular species in an atmosphere due to concentration, pressure, and temperature gradients. Very briefly, viscosity and thermal conduction, these two have been discussed and have been studied by several papers. Sharon, Fedorenko, there's many different scientists who have paid attention to this. So we're thinking like frictional forces of a gas, and we're thinking like when there's collisions and temperatures go from hot to cold. And then when we talk about species diffusion, we're discussing something that's somewhat new. Again, we have these different species in the atmosphere: nitrogen, oxygen, atomic oxygen, and they behave differently when they are exposed to temperature gradients and pressure gradients and concentration gradients as well. I'll talk about two very briefly, but pressure gradients are when there's a movement from high to low pressure for a species. So if you have a massive gas, it will tend to move towards higher pressure places, and if you have a less massive gas, it'll tend to move towards low pressure. And temperature kind of works in the opposite way. So there's these I can describe this phenomenologically, but the description of them in terms of mathematics gets a little more complicated. But we could say that these transport properties depend on the frequency of collision. So viscosity and thermal conduction, these describe with frequency. They depend on the frequency of collisions. These are temperature dependent. So you can say these are sort of related to each other, but species diffusion relates to the nature of the collision and the description of the molecules themselves. And previous studies have really done single or binary gas descriptions of an atmosphere. So they haven't really included species diffusion. And here is a key one by Sutherland and Bass in acoustics. They're saying that it's 0.3% of the species diffusion is basically not even included in it because the atmosphere that they modeled after was nitrogen and oxygen. They have similar properties. There's not as much movement of the gases individually. So one of my thesis expressions was focusing on developing expression for species diffusion and investigating what it does to an atmosphere. And you can see that the assumptions from below, or from the previous study, where they only had nitrogen and oxygen, is valid for the lower atmosphere, but above, it has the mixture of atomic oxygen included. So again, how does a species diffusion, how does the multi-component nature of a gas affect acoustic wave propagation? I'll briefly go through the math to how we can answer that question. So we assume a continuum, being defined by a Knudsen number. So Knudsen number describes the sort of the mean free path flow or the distance between collisions. In the upper rarefied atmosphere, there's a larger distance between collisions, so you would call that larger Knudsen number. For our studies, anything probably below 300 kilometers is probably sufficient, but it depends also on the atmospheric conditions. You can assume things are close to thermodynamic equilibrium. This is how the diffusion equations that we're using are valid. So then we have the sort of what you can call the multi-component Navier-Stokes equations. These are when you apply this to a single component gas. So let's say you just have one that has nitrogen. This becomes the Navier-Stokes equations. And on the left, we have the Euler equation. These describe the movement of the gas. Like think of the continuity equation. That's part of the Euler equations. Change in mass over time should equal to the net flux in that region. And then you have one for the energy equation. You have one for the momentum equation as well. This is Newtonian, so there's nothing sort of novel introduced here. The novelty is in the right-hand side, which is the transport fluxes. So again, if you put this in a single component limit, you get the Navier-Stokes equations. But because you have a multi-species gas where you're including all the effects of the species intertwined with each other, you get more things then. So I have a lot of colorful stuff here. The top one is already included in the Navier-Stokes, and then Fourier's law is also included, but the other 1, 2, 3, 4 are not. So we have concentration diffusion. That's diffusion due to the concentration gradient, pressure diffusion. That's for the pressure gradient, and thermal for temperature. And then this affects the energy equation as well. And with these equations comes these transport coefficients. These are based off of a linearized algorithm by Erning-Joe Angeli. Prior to this, most of the expressions were empirical. So they were empirically derived for the viscosity coefficient and for like thermal conductivity, etc. Here's an example of one. So you solve this linear system. It's kind of tedious, but it has advantages is that as long as you have the properties of the gas, you don't have to, everything is defined self-consistently. And also another benefit is they're introduced into numerical models with relatively low cost. I put a lot of asterisks there because it's kind of not true. So we'll go into linear theory, and then I will go into nonlinear theory, which is the modeling part. Both are important for doing any sort of analysis of a wave. Linear theory has been done by like doing dispersion relations, by quantifying wave numbers that are typical to acoustic waves or acoustic or gravity wave studies. So I'm just going to walk you through the steps of what I did and then the results. For any linear theory, you can separate your wave into two parts. So there's the ambient part, like the background atmosphere, here described by Q0, and then the perturbation. So if you have a small perturbation to your system, that's described by Q1, that is your perturbation. And if you separate things, if this is the premise of it, then you can apply several analysis. You can assume plane wave solutions and you get sort of a nice Fourier transform system where you can do ray tracing, etc. If you're trying to incorporate more physics into it, you have to do what's called WKB approximation. So for your equations, you have like these coefficients that are not constant with altitude, which you can assume so with this approximation. I have an example linearization where it goes from the sort of the 3D version to, again, it's very tedious. As a matter of fact, it gets much more tedious than this. This is a matrix system that you can get from linearizing the equations. This is for a non-dissipative one, though. The one that is with all the coefficients included is huge, and I did not include it. So you get a dispersion relation. If you do it with the non-dissipative part, that looks like this. The gravity part in the middle, G is for gravity. That makes it non-linear. And so there's no dissipation here. When you add dissipation terms, thermal conduction, viscosity, you get from the above, the fancy K squared, plus some other terms which are associated with attenuation and phase. And if you include the new coefficients, then you get even more. So everything is additive, and you get these, again, a somewhat massive sort of dispersion relation, but these coefficients are important because they tell you about the attenuation of the system. Here's a figure of the frequency with wave number, and you can separate the acoustic and internal gravity regimes based off of this, just like I showed you in the beginning. This is derived from a dispersion relation with no dissipation. I want to focus on the acoustic part first, and then I'll go to the internal gravity wave ones. Here we have the attenuation part again. So I described that earlier. That is as a result of analyzing the imaginary part of the wave number. And for these attenuation parts, this is only for acoustic waves. But again, this is that damping part. This describes the spatial damping of a wave based off of the characteristics it have. Yeah, the classical part, which is viscosity, thermal conductivity, and bulk viscosity, and then you have what I'm deeming new is species diffusion. So in our paper, which has been submitted, hopefully it'll be accepted, we have the right-hand side. So this is the classical one. This has been done since the 1800s. And then in the new part, I have an sort of a generalized species diffusion equation. So this was derived in our paper. There has not been any update to this since the 1940s. So this is at least the coolest part of what I did was, or what our team did, was update something that had nothing, sort of never been visited since the 40s. On the left is the species diffusion term for a binary gas. So let's say you have nitrogen and oxygen, and ours is for as many gases as you want. It describes the interactions between the molecules and how it dissipates energy. And again, I want to emphasize, even on the 2024 paper, the species diffusion term has been ignored. And they based it off of the 40s expression. So here I am advertising it. So we have a species diffusion term for various atmospheres. I'm going to quickly go through this. We did it for Earth, Venus, Mars, Titan, Neptune, Uranus, any atmosphere where we have like the molecular information for, then we can do it. So for Earth, I chose an atmosphere that had a lot of helium towards the top just to demonstrate what species diffusion could do. Here's a Knudsen number again, and so it kind of bottlenecks as you go up because it's rarefied, but this atmosphere was especially dense and cold. So you get this is sort of what a typical atmospheric absorption coefficient looks like. So the blue is low and red is really high. These lines represent when the attenuation is 10 to the minus 2, or when the attenuation is 1 decibel per kilometer, which is a lot. It has sort of, as you go up in altitude and higher frequency, there's more attenuation. Now that makes sense, because if you have a wave that's moving a lot, then you get more chances of particles colliding. More chances of particles colliding means energy dissipates. So here we have a plot of the percentages of the total attenuation. So the black line to the right is due to viscosity. That has been studied forever, and that's known that it's the biggest contributor to attenuation of a wave. We also have thermal conductivity, which is the next line to the left, is also high. But the species diffusion term, which I have a couple boxes around, that increased from 5%, which before it was predicted to do nothing. It was depicted to be negligible. And this is all due to the pressure diffusion. So there was 3 that I named: concentration, pressure, and temperature. And all of this, and for every atmosphere analyzed, is all due to pressure diffusion, because you can separate and see which one is affecting the wave. For Venus, we have a similar idea. So I chose 2 atmospheres, because they show different characteristics, and I can really show you the effects of species diffusion. In atmosphere 1, we have this sort of profile. They're both similar, except one is denser. The number 2 is denser. And the biggest difference is, you can see here, these are mass fractions of the first and second. The first one has tons of atomic oxygen, and it remains that way. The second one gets more oxygen, gets more helium and hydrogen as you go up. So these lighter molecules, when they interact with heavy molecules, you get more interactions between heavy and lighter molecules, and more energy is dissipated. This affects the condenser number as well, but I'll skip over this for now. Similar absorption profiles as for Earth, so this is fine. This is what was expected. But the main takeaway is, if you have this species diffusion term, it goes up to 15% on the atmosphere 1, where there's a lot of atomic oxygen, but it goes up to 45% for the atmosphere 2. So this takes into account a lot of the interactions between these molecules. And it goes highest when there's these differences between light and heavy molecules in the top. And so at that region, there's a lot of hydrogen, a lot of helium, still some traces of carbon dioxide and nitrogen. So there's a lot going on there. I added an exclamation point because this is a cool finding. For Mars, we did a similar analysis. In the paper, actually, we go up even higher, but the main crux is, you can see at the top towards 175 kilometers, we have atomic oxygen, we have nitrogen. So there's this quaternary mix of molecules, and you get, again, 15%, or actually maybe even higher, of the species diffusion term. So this new sort of expression has an effect, and we need it to be a multi-component one, because if it's a binary one, we're misrepresenting these atmospheres. This is very brief. Actually, this is vibrational relaxation. This is another way for energy to be lost. This is when there's polyatomic molecules and they're heated up, they will start to lose energy to their vibrational modes. So this is like carbon dioxide, nitrogen, etc. In Earth's atmosphere and Mars, they're important below 100 kilometers. On Venus, they're important below about 130 kilometers. So this is just to contextualize it, because of the alpha total here includes all the dissipative processes that could affect the atmosphere. So this is just to contextualize that our findings are still valid, especially in the upper atmosphere. I want to go briefly into numerical solutions, and hopefully I'm good with time. I work with Jonathan Snively, and he had produced the MAGIC model. This is for solving actually 1, 2, or 3D problems. It's like a finite volume method, and it resolves small scales. So I know a lot of people here are maybe used to bigger scales, but this is for smaller scale waves. But hopefully it can be integrated or adapted to solve both. Magic has similar restrictions to a finite volume method. So we have a CFL number. Information cannot travel faster than the actual discrete package, or it can't travel faster than the actual wave itself. So there's a restriction there. Fourier number is not really a restriction, but it slows down numerical, or it defines how you can do like the dissipation portion. And if you're adding chemical reactions, then your delta T has to be way smaller than the relaxation time or the chemical reaction time. I have a photo of like a discrete grid, but essentially this describes I call them rules, but these are just kind of like restrictions on modeling with magic. The algorithm for magic is, I'm simplifying it here, but if you have a background atmosphere or an atmosphere or some sort of initial condition, you have to have these boundary conditions to define your source. Sorry, your scheme, define a source. So if you have like a Richter wavelet for impulsive sources, or you can have something sinusoidal for something in a steady state, it depends on your problem. And then you can just run the main algorithm, which is you update the equations or advance them. You update the transport coefficients. You solve for the dissipation on them, and then you just do it again and again and again and again. Here's an example. It's like if you have heard of this 2011 Tohoku earthquake source, here are some like observations from it. You can take these observations, you can parametrically try to match them. So parametrically meaning you could just change some of the numbers, let's say the red numbers, try to adjust them to match whatever source you have. You can of course do this too with like real numbers that are derived in these observations. Like I'm sure they took a Fourier transform here or something, and they got some like prominent wave number, but you can have a source. This is a sinusoidal Gaussian. So this describes, here's a pulse that dies down with time or in space. So you have the ability to change different values, and especially if you're doing 1D modeling, then you can kind of play with the toy model. And so that's actually my attempt at a smooth transition of these parametric sources were from this case that I did. And here I'm including the species diffusion part. So this is the 1D Tohoku test from the 2011 earthquake. There's a paper already done by Zettergren and my advisor, and I updated the model that they used to include the species diffusion term. So they have their solution, which thermoviscous, meaning with viscosity and thermal conductivity. And I have my full system, which includes a species diffusion. And you can already kind of do a similar match here, but the main point is that there's more downwelling, there's more dissipation from the one on the right, which is the updated model, versus the one on the left, which is the one from 2015. Here is some sort of overlaying results of them, where the x-axis is time and the y is velocity. The black line has no dissipation. The purple line has the full system. And I just played around with these. So this might be a little confusing because there's a lot of different lines, but there's some differences in phase and in the amplitude, which is primarily the purpose of this. And this is at an altitude of 400 kilometers. And when you track how the species moves over time, the black one again has no species diffusion. The purple one has everything in it. So there's some differences here. For another case, the Tohoku case was a large case, as in like the vertical velocity went significantly. And for a long time, this is another case where the source was designed by to simulate a bomb or a TNT equivalent yield source, a bomb. And so it's at very fine resolution. This is at 4 meters. So this is a different type of simulation. Dimensions, actually symmetric. The first one was 1D, kind of a toy. The velocities reached here are not as high. So how does that affect? How does species diffusion affect it? Well, we have here this is kind of hard to see on the screen, but we have a black line, which only includes the thermoviscous parts, and then we have sort of like a teal or slate gray line that includes everything else. For these sources, it's affected maybe by like 5 or 6%, which was what was predicted in the acoustic source. This is a source of acoustics, so this makes sense. It follows what I got from the linear theory. I'll subtract how the atomic oxygen moved, and it changed by similar proportions. It's not significant in this case because it's lower speeds. And we also tried sort of, this is a case where you can insert some sort of Gaussian source and get internal gravity waves. Towards the top, around 300 kilometers on the left, you can see those are some clear acoustic waves, and then towards 100 kilometers, you're seeing gravity waves sort of doggy paddle their way up. And then you have the same analysis that I did before. Here, for gravity waves, does not affect the species diffusion part. Again, showing this sort of slate gray dashed. It's not affecting it much, but it changes it by about 5%, maybe less. But there's still some hope for, or at least some desire to go further. Maybe we could apply this sort of modeling to Venus. Here I pretended to insert some earthquake source in Venus, and I saw, this is interesting. You could do the same thing for Mars, and you can see how the different atmospheres affect it. I'm not sure why it's ringing so much there, but there I put all the species, and I just kind of let it go and see what happens. We can include more chemical reactions. We have some chemical reactions already, but can include some more. Just to conclude the talk, we have just presented to you about the sort of the implications of what a multi-component atmosphere can do in terms of the acoustic waves, in terms of internal gravity waves preliminarily, and describe how transport coefficients can be described on Earth and other planets. And that's it. Thank you.
Any questions?
For earthquakes and Venusquakes, like, do you have any data to compare with? Maybe I should go back to the like 50%, 45% change in your molecule. You have spatial diffusion.
Oh yeah. So right now, no, especially for like Venus, there's no acoustic waves detected on Venus. So a lot of this is sort of theoretical dreaming, but the idea is that if they design some sort of space mission, then they would include these effects. They have stuff, I think, near the ground or something. I've seen some studies like that, but this is all for like the upper atmosphere. So
The mainland data, you're not able to compare with these results.
So I've only looked into Venus like the most. I included Mars because that's been a hot topic for people too. So I was actually really, just to be very frank, very interested in Venus because it was the highest, and also there's a lot of different there has to be a lot of dynamic going on there. So, but I will look into Mars. I probably should.
Any other questions?
For the results, say for Earth, how sensitive is it to what you specify for the background atmosphere?
Especially above 160 kilometers, because and I did this actually. I did it like a sort of a parametric study. Depending on how cold it is, you can get a lot of helium, like somewhere around 300 kilometers. So it'll get, species diffusion will shoot up pretty high. If it's near like the lower thermosphere, it's the same. So it's about 5%, and I think that's how it remains. I added like 12 species, and it stayed the same. So
I guess I mean, even if you have like 10% or 20% error in how you specify the composition,
I see.
would that matter or not really?
No.
Okay.
No. Well, below 200 kilometers, no. I think above, it just depends on how much of the lighter species you have. So, but yeah, if you're if you're like saying there's like 20% helium for some reason, it'll significantly impact it. Because even like I can even show just part of it. Oops, that's additional slides. Part of it. Yeah, it's cut up to, where is it? Yeah, about 15% at the top.
Mhm.
That's only due to, I mean, barely any helium there.
Okay.
So this is like the most extreme case though. So it'll be sensitive to those lighter ones, I'll say. It won't be, if it's down here around 150 or 200, it's not. It's fine.
So you said that the fact that it's more pronounced on Venus,
Yes,
the diffusion.
yes.
Then can you just go back to it?
Oh, yeah, sure. Up here. And here's the composition. And yeah, as I said, like it'll be sensitive to these things. And then, yeah,
So the diffusion is more pronounced at high altitudes on
yeah.
Venus. And have you looked up like how that affects the global flow on Venus?
Well, this is the going back to the comparison of data thing. There's not, so this is for acoustics only.
Mm-hmm.
And there's not any acoustics measured, especially at those altitudes. There hasn't been anything measured yet.
Because I know Venus is an interesting case of superrotation that the rotation rate raises as altitude.
Yeah.
So I don't know, maybe something to look out. That's
Yeah.
in relation to that two things.
Well, I could probably do a simulation and then just be like, this is cool, guys. But if I don't have any data, then I don't know how accepting the community will be about it. But I think it's cool.
Makes it easier.
Yeah, well, I'll say this, that preliminarily, and I'm not hyping this up, but preliminarily, like viscosity and thermal conduction, the effects were derived in the same way as the species diffusion part. So we can assume that if we could measure the dynamics, that we would have to incorporate it, depending on the composition of Venus, but it's irrelevant. It's relevant to these altitudes. So I would say wait for the JASA paper. Hopefully they'll validate it. Yeah, anyway. Anything else?
Any other
questions?
So when doing simulations, generally want the numerical diffusion be really small compared with the physical viscosity or dissipation. Have you done any tests to make sure it's the case or?
Oh, for the numerical, yeah. So that's part of the magic model, which I had to like go through, but they already have like within the magic model, it's already resolved its numerical diffusion. It has I know it has like some sort of like TVD criteria, and it has the way it's set up, it takes into account numerical diffusion. I don't, if you want to see on my thesis, I have some sort of tests for it, but I did that like a couple months. I didn't include that here. But it should be okay. I mean, John has been using this model for like 20 years, so.
Any other questions? Or from online people?
What's your plan for next?
Oh yeah, I guess. And so, actually less than a week, I'm going to Italy. And I just saw,
The development.
Oh. my personal life.
So,
Yeah, oh yeah, so, don't worry, this is not aerosols. But so we have this multi-species model now, so we can include as many species as we want. And this meaning that like we can incorporate their like molecular properties. So TMAs have been used as rocket tracers, and part of this Vortex project is to model how it disperses in the upper atmosphere. So you have this sort of here's like this glow of PMA as it interacts with oxygen. You can assume a gaseous form, so I won't talk about the aerosol part, but you can assume a gaseous form of it, and then it has its own diffusion properties. And you can say that either it interacts with the major gas and how it disperses precisely. So that's sort of been the next step. And also, I'm looking to like do some sort of Venus research, maybe some Mars. Depends on how the planetary world is, but I want to include like on Venus. I have here a photo. Yeah, I just wrote. Where is it? I just wrote clouds for see around 50 kilometers. I just wrote clouds, but that has tons of different. I mean, that's sulfate probably in there. So how does species diffusion affect that? Well, what's make it more chemical, I guess. That's sort of my next steps. Oh, and trying to use Wacom combined with magic. Cool.
If there's no further question, let's thank the speakers again. Thank you.